Part 2, geometry. So today we'll talk about how to find the area of a very complex shaded area. We will use techniques such as divide the existing graph into smaller polygons, or we'll add extra parts by extending existing sides for forming a new polygon. We'll learn this through practice problems. First one, practice problem 13. The area of the below equilateral triangle is 36. Find the area of the maximum inner hexagon. Maximum inner hexagon, basically the hexagon has to be maximum in area, so it has to touch the sides of the equilateral triangle. Okay, because the hexagon has a property that all sides are equal. And when it's touching, this is equilateral triangle 2. So all these sides has to be equal. Okay, therefore, this is 1/3, this is 1/3, this is 1/3, and so on for all the other sides. Okay, then we can use extra lines to separate the shaded area. So if we draw these 3 lines, then you will find that this is equilateral triangle, and so are all the rest of the 5. And since this side equals to both sides of this, and this is equilateral triangle, so this 3 sides would be equal to. So this triangle is the same as this one, so are all the rest of the triangles. So they are all equal triangles. So how many are those? 1, 2, 3, 4, 5, 6, 7, 8, 9. You have 9 triangles equals to the total area of 36. So each triangle has an area of 4. So now you look at the shaded area, how many triangles are there? 6. So the total 6 triangle would be 24. Practice problem 14. Find the area of this. Okay, this problem, there's the most straightforward way is to add the triangle to the trapezoid. Trapezoid, you have the height here, you have the base, but the top, this is unknown. So we can try to find this one out. How do we find that one? If we add one line here, this is a right angle. You have side of 13, and this side is 12. What is this height, this little thing? So remember, we have, for right angles, the longest side square equals to one side square plus the other side square. Okay, this is 169, this is 144. So this side is, if this side is 5, that is 25, this thing will equal. So this side equals to 5. And now the remainder is 7. So this is 7. So basically the total area is the triangle plus the trapezoid. Triangle is 1/2 the base multiply the height. The base is the same as 5 because this side is 13, this is 12. So this little side has to be 5. So the base is 5, multiplied the height is 12, plus the trapezoid. Trapezoid, we know that is 1/2 the top plus the bottom, multiply the height, that is 12. So in this way, you can figure this, you can find the area this way. So the total would be 144. There's another way to solve this problem is if you look closely, change the color. This triangle has a side of 13, and this side is 12, which is the same as this. If we use this point as a pivot point and we rotate this triangle to here, the longest side 13 is going to match this longest side 13, and this side becomes horizontal, that's 12, that equals to this. Now you don't have to do the triangle area. The triangle is being rotated to here. Now what you have to find is the area of this rectangle. What is the area of this rectangle? It has a side of 12. It has a height of 12 as well. So 12 by 12 is 144. So this is the second way of solving this problem. Problem 15. ABCD is a square, and BEF is isosceles right triangle. MN is the middle point of side AD and CD, MN. The area of the shaded area is 14. This area is 14. Find the area of triangle BEF. Looks like it's a pretty complicated problem, but again, we can add additional lines to help us separate this into smaller areas. So if we have okay, if we do this, now let's look at closely of all the right angle triangles, whether they are the same. So these two are the same, these two are the same, these two are the same because they're just splits from the little square. This ABCD is a square itself. So we separate the squares into squares. So all these little triangles are the same. Let's look at whether this one is equal to this. Okay, isosceles right angle. This equals to this equals to that, and right angle. So these two triangles are the same too. And because these two are the same, and let's look at these two. We have isosceles right triangle. This side equals to this side equals to this side. So this triangle has to equal to this one. So we can prove that all the little triangles in these cases are all the same. Let's count how many are those. 1, 2, 3, 4, 5, 6. Okay, let's look at this in a more systematic way. 1, 2, 3, 4, 5, 6, 7, 9, 8, 10. So we have total of 10 little triangles. And we wanted to find out the area of BEF. BEF, there's a total of 9 triangles. This is the number we wanted trying to find out. For the shaded 1, 2, 3, 4, 5, 6, 7 triangles, the total area is already given you. That's 14. So each triangle has an area of 2. So for BEF, that what you find is you need to find 9 triangles. So that's why the number is 18.